Today we are going to discuss about Euclid's algorithm for finding GCD of two numbers. It's a very efficient algorithm. First we shall state and prove the GCD Recursion Theorem, based on which Euclid proposed this algorithm for finding the GCD of two numbers. In a naive way, one can find the GCD after finding the divisors of both the numbers and then finding the maximum from the intersection. That is what we show as the definition of the GCD. But the algorithm that we are going to discuss today finds the GCD in a clever way, and which results in an efficient algorithm for finding the GCD. So the topic for today is Euclid's algorithm for finding GCD. Let us recollect the basics that we have recollected from number theory. In lemma 1, we proved that if D divides both A and B, then D divides any linear combination of A and B. That is, A multiplied by an integer plus B multiplied by an integer for all integers x and y. So lemma 1 says, if D is a common divisor for both A and B, then D divides any linear combination of A and B. Then we stated and proved this theorem, which tells us that for two integers A and B, such that one of them is non-zero, then GCD of AB is the smallest positive linear combination of A and B. We proved this theorem in the last lecture. So if you can please remember what is theorem 2 saying, the GCD of A and B is the smallest positive linear combination of A and B. Now from lemma 1 and theorem 2, we can have a corollary. What is the corollary saying? If D is a common divisor for A and B, then D divides the GCD of A and B, because by theorem 2, GCD of A and B is a linear combination of A and B, and by lemma 1, the common divisor divides any linear combination of A and B. So corollary 1 follows. Hope you can remember these three results. And now we can look at the GCD recursion theorem, which allows us to get this algorithm proposed by Euclid. Theorem 3 states this: for any non-negative integer A and a positive integer B, GCD of A and B is same as GCD of B and A mod B. A mod B is the remainder of dividing A with B. So here there are two assumptions about the numbers A and B. We can see that these assumptions are fair. These assumptions are fair since we know that GCD of A and minus B is same as GCD of A and B. So you can just discard this symbol, sign. And GCD of A and B is same as GCD of B and A. So from these two, it is evident that you don't have to worry about the non-negative numbers, because if it is negative, you can just discard that sign and we can just find the GCD of the absolute value. And second assumption, it's a positive integer. So meaning it's not 0. We are not interested in 0 because we also know from the previous lecture that GCD of A and 0 is A itself. That is what we saw in the last lecture. Easy to verify this definition also. So we are not going to worry about the case when B is 0 because then it is directly defined as A. So we are going to prove this theorem for this restricted values of A and B, which is actually not restricting anything because we saw that it's not in fact putting a restriction. We need to prove the theorem, and for that assume that D1 is representing the GCD of A and B. D1 is the GCD of A and B. Then D1 divides both A and B because it is a common divisor, follows from the definition of GCD. And we can have A mod B, which is the remainder of dividing A with B, as A minus B multiplied by the quotient of dividing A with B. So this follows from theorem division, which tells us that for any A and B we can have this equation. There exists a quotient and a remainder such that A is nothing but the quotient into B plus A mod B. So from this equation you are obtaining A mod B as A minus Q multiplied by B, where Q is the quotient of dividing A by B. Now from lemma 1, if you recall, we know that D1 divides A mod B because we know that A mod B is a linear combination of A and B. Why is it a linear combination of A and B? Because A multiplied by 1 plus B multiplied by minus Q. So A multiplied by 1 plus B multiplied by minus Q is A mod B. So A mod B is a linear combination of A and B. Then from lemma 1 we know that D1 divides any linear combination of A and B and hence A mod B, because A mod B is now written as a linear combination of A and B. Now we have these two results, D1 divides B and D1 divides A mod B. Now from corollary 1 we can say that D1 divides GCD of B and A mod B. Why? Because we know that from corollary 1, if D1 is a common divisor for two numbers, then D1 must be a divisor for the GCD of that two numbers. That is corollary 1. Sorry. So we are telling that D1 is a divisor for GCD of B and A mod B. What is D1? D1 is nothing but the GCD of AB. So just substitute D1 here. You are getting GCD of A and B divides GCD of B and A mod B. And not that we have to prove they are equal. One part is done. Now let D2 be the GCD of B and A mod B. So previously we found with this assumption that D1 is the GCD of A and B. D1 is LHS. Now we are assuming that D2 is the RHS of this equation. Then no doubt D2 divides B and D2 divides A mod B, because GCD is a common divisor for both B and A mod B. So from the definition of the GCD, D2 must divide both B and A mod B. Now from the division theorem, for any A and B, we can write A as B multiplied by the quotient of dividing A by B plus the remainder of dividing A by B. This is division theorem. Exactly this is what we are using here. Now, lemma 1 tells us that if D2 is a common divisor, now lemma 1 says that what if we have a common divisor D, then D divides any linear combination of A and B. So here is not that A is written, A is written as a linear combination of B and A mod B. B multiplied by an integer plus A mod B multiplied by an integer. This is exactly what A is. So no doubt A is a linear combination of B and A mod B. Then from lemma 1, D2 divides A because D2 divides B and D2 divides A mod B, and hence from lemma 1 D2 must divide any linear combination of B and A mod B, and now A is written as a linear combination of B and A mod B. Why is a linear combination? Because B multiplied by an integer plus A mod B multiplied by an integer. So that is correct. And now from corollary 1, which says when D2 is a common divisor for A and B, then D2 must be a divisor for the GCD of those two numbers. This is corollary 1. So we have this. Now what is D2? You substitute the value of D2 which is GCD of B and A mod B. So we are saying that GCD of B and A mod B divides GCD of A and B. See, now you see these two results. You are here saying GCD of A and B divides GCD of B comma A mod B, and here you are proving that GCD of B comma A mod B, that is the RHS of this equation, divides GCD of AB, that is the LHS of equation. So we proved that the LHS of this equation divides the RHS of this equation, and also that the RHS of this equation divides the LHS of this equation. So this happens if and only if they are same, and hence proved. So what we proved? GCD of A and B is nothing but GCD of the second argument comma A mod B. First argument mod second argument. We can just apply this to get what is called the Euclid's GCD algorithm. We know that GCD of A and B when B is equal to 0 is A, which we know. So that is the escape condition for this recursion, and otherwise you just apply the theorem 3 that we just proved. We know that GCD of A and B is nothing but GCD of the second argument comma first argument mod second argument. So that is the algorithm. So algorithm is very simple to look at, but to have this algorithm we need to have theorem 3. And to see how efficient it is, let us look at an example instance to this algorithm. So what is Euclid 3021? 21 is not 0, so it is Euclid 21 comma 30 mod 21 is 9. Again you apply, it is nothing but Euclid 9 comma 21 mod 9, which is 3. Now again it is Euclid 3 comma 9 mod 3, which is 0. Now you are getting the escape situation, so you can define this as 3. So not that in just 4 calls you found the GCD of 21 and 9. And with this we are coming to the end of this lecture, and I am giving you a homework exercise for you to understand how efficient this algorithm is. You can prove that if A is greater than B and B is greater than or equal to 1, then this is an assumption that we have about the theorem 3. Then we call Euclid AB performs k number of recursive calls. In the previous case k was 4. Then you can prove that the value of A must be greater than or equal to the k plus 2th Fibonacci number, and the value of B must be greater than or equal to the k plus 1th Fibonacci number. And if you prove this theorem, then you can say what is the complexity of the Euclid's algorithm for finding GCD. Today we have proved the GCD recursion theorem, which tells us that GCD of two numbers A and B, where A is non-negative and B is positive. So GCD of A and B is defined as GCD of B and A mod B. We proved this theorem, and which is proved by Euclid, and proposed a recursive algorithm based on this theorem, which is a very simple algorithm with just 3 statements and is very efficient also. Thank you.